A beautiful example of using diagonalization for the good of humanity, cats, monks, the universe, is computing the nth Fibonacci number. Why not? That's a fun thing to do. So Fibonacci, who was not the person who originally thought of this sequence, but apparently did so in trying to understand how rabbits were multiplying. Could have used another method, but this is a simple idea, right? So that a number in the sequence is the sum of the two preceding numbers, and we start with 1, 1. Right, so we'll label the first one as the 0th one in good computer science approach to things. But it does have predecessors, and of course, this fits in with Stigler's rule of eponymy, which is that no law, that's a law actually, so no law or rule is named after the person who actually thought of it, including Stigler's law of eponymy. So just look that one up. All right, yeah, very nice. Okay, so right, so we've got this thing. I've laid this out before in an earlier episode. So we have capital F's for the numbers themselves, for the Fibonacci numbers themselves, and then we'll write a little vector, just a 2x1 vector. We'll just stack adjacent Fibonacci numbers on top of each other, and we derive this nice little thing here, which is that if we want to go from fk minus 1 to fk, we just multiply by 1, 1, 0, 1, 0. So this matrix, a lot of things happen in this matrix. It's kind of crazy, very simple, just ones. There is a nice piece, which again, note symmetry. We're not going to capitalize on it right now, but that is always a good thing. And let's see, right? And so if we keep going down, we figured out that, in fact, the kth vector would be the 0th vector multiplied by this benign little matrix to the power of k. So we need to understand that thing. And the first one is just 1, 1. Right? Yep, good. So our mission is to diagonalize this matrix, right? We're going to diagonalize. We love the diagonalizing. It's pretty good. It means finding eigenvalues, eigenvectors, stacking them the right way. We can, so I'm just going to step through this because it's a good thing for you to work through. We find the determinant of, right? So normal approach, as usual thing. We want to find the determinant of this associated matrix, A minus lambda I. So it gives us a very famous equation, actually, quite famous, very famous. We're just going to set it up in this thing. I'll talk about it a little bit, but and you solve this, you find lambda 1 is 1 plus root 5 over 2, and lambda 2 is 1 minus root 5 over 2. So these are numbers whose magnitudes, right, so the one with the largest magnitude is the one we'll assign first. This is actually the golden ratio. So kind of a crazy thing. The Fibonacci numbers have the golden ratio floating around inside them. And just a little aside here, where should I put this? Yeah, let's put a little aside up here. Rho equals 1 plus root 5 over 2. 1 plus 1 over 1 plus 1. This is a joyous thing. It's continued fraction. And from this you can see, so this is continued fraction, expansion. It's the most irrational number. It takes the longest to converge. The most irrational number. Beautiful. A beautiful thing. Right. It's also the ratio, you can, same idea of the rectangle that people got very excited about and thought was the best one. Maybe not so, but you know, the golden ratio is there in lots of places. Spirals, in the number of spirals in, say, a sunflower or pine cone, right? If you count the ones going one way and ones going the other way, they turn out to be generally the adjacent numbers in the Fibonacci sequence. Beautiful thing. There's some fantastic work from the late 1990s of Yves Couder and Duardi. You should look that up, where they made little simulations of this. Really great. So it's a universal truth. We always like those things. Okay. If you be a little careful, you can play around. You can do things in good and bad ways. So you can figure out that this is you can make a horrible mess here, right, with root 5s all over the place. But this is not a bad thing to do. Figure it out. So this is sort of a good hygiene, right? Not too messy. Keep root 5s at bay, right? Fairly, and we'll bring them back later. Yeah. Just a couple of these sneaky tricks that we've checked, right? So if we add them together, the eigenvalues, then we get 1, and that's the trace, right? The trace of this thing, 1 plus 0. If we multiply them together, we get -1. You'd have to look at that a little bit, right? There's 1 minus 5, which is -4 divided by 4, so it's -1. And that is the determinant. 1 times 0 minus 1, so it's -1. So these things check out. All right, just little pieces there. But then we basically go and set up everything. All right, we've got our 3 pieces, the eigenvalues. We're just going to leave them as lambda1, lambda2. Our eigenvectors are set up like this. We find the inverse of that matrix. We compute all these good things. And then we can raise our original matrix to the power of k. Right, this will be, this is A. This is A. This is S. This is lambda to the power of k. And this is S to the -1. If you multiply all those things together, and then also multiplied by 1, 1, right? So this is our initial piece, so we're talking about here, right? Yep. Then you get this result. This is, right, this is a 2 by 1. This is a number here divided by a number. I'm sorry, a number in the first entry and a number in the next entry. It's not a 2 by 2. Maybe I should make that clear. Not a 2 by 2. Right, this is a number and a number. Hopefully that's okay. So the top one here is the k plus 1th entry, and the bottom one is the kth entry. So if we want, we can say we get this result here. So this is let's do this. This is a pretty cool thing. It's a delicious result. So we've kept the lambdas all the way through to the end. We just have a lambda1 minus lambda2 on the bottom. That's not bad. Actually, it ends up just being root 5. The 1's cancel, and we root 5 over 2 minus root 5 over 2, so it's root 5. This is delicious. And if you look at this thing, you can see that this piece this will dominate, and this one will disappear. And it's quite small for small k's, actually. So it's in fact true that the kth Fibonacci number is the integer part of this, which is okay. But in fact, all of these root 5s will clean themselves up. Beautiful result is that it's just growing as the power of the golden ratio to the power of k. So the ratio of adjacent Fibonacci numbers ends up just being that first, right? This is lambda1. The first eigenvalue, that's how it's growing, lambda1 times lambda1 times lambda1, which is the golden ratio. So that is a beautiful thing. You should figure out the details for this, and it's great. Okay.